focus more on the dry temperature. So really on the observations, and not to mix too much background information.
Thank you, Andrea.
Thank you.
I would like to invite Julia Dancer. She's our second speaker, and she'll talk about the potential of radio occultation data for climate, wind field monitoring, and overview of latest results.
So good morning, everyone. I'm Julia Danzer. I'm also from the Wegener Center from the University of Graz. And I'm going to talk with you about the topic I have been lately really passionate about, which is the potential of radio occultation data for climate wind field monitoring. And I really aim to give you an overview of the latest results because there has been a lot of work going on within my research team, which, so the people who were involved are Irena Nimac, Magdalena Pieler, and Johannes Unek. And Gottfried Kirchengast was also part of it as a scientific advisor. So the question is, of course, what's the motivation for doing wind field monitoring? And as you may know, most observational-based techniques either show a very high vertical resolution or they have global coverage. But most of them, not all of them, but most of them lack one or the other. This leads to kind of more sparse profiles over specific areas like the oceans, the southern hemisphere, over the equator, for example. So, I mean, you are all experts, of course, in RO. But as you know, so RO data has some properties like it has global coverage, so that's good. It also has this multi-satellite coverage option, so with no need of intercalibration. It has actually a very high vertical resolution of atmospheric profiling. And also very important, it is essentially independent of cloud influences. Like, for example, the Aeolus mission, it depends on clear air molecular scattering. And also, you know, the best accuracy is in the upper troposphere and lower stratosphere. So, of course, when we talk about RO data, we cannot measure wind, we have to derive it. And this means we depend on physical equations. So what we did, we looked at different approximations of the momentum equations, which is the geostrophic balance. It's a balance between pressure gradient force and Coriolis force. The gradient wind adds also the centrifugal force. Then there is the equatorial balance, basically the Coriolis force. When we go towards the equator, it converges towards zero, meaning that we have a singularity in the solution. And we need another solution, which is the equatorial balance equation. Here I want to emphasize that Sean Healy has looked at the equatorial balance equation as a zonal mean in the stratosphere. What we did, we computed the zonal component and the meridional component, and we really looked at wind speed. So when I'm talking about climate wind field monitoring, I'm always thinking about the free atmosphere, I have to emphasize. So friction is not relevant. Yeah, and I'm using monthly data. I should maybe mention that as well. And I want you also to give a brief outlook on including advection to the solution. So what we did is basically we used ERA 5 data from the period of 2007 to 2020. And in the same period on this monthly 2.5 times 2.5 grid, we used the multi-satellite RO data from the Wegener Center. And we did a two-step approach. That's actually for me really important that you understand that. We did, as a first step, we computed the wind fields based on ERA 5. So basically we downloaded the ERA 5 data and we computed also wind fields using the physical equations because we wanted to understand the quality of the approximations. So what's the approximation bias? That's the question. So we want to get an idea how good is the approximation. And in the second step, we of course computed the wind fields also for our data. And we basically studied the bias between the two data sets. So both derived from the physical equations. So to get an understanding of the systematic difference between the data set. And not mentioned here, the total bias relative to error was of course also investigated. Yeah. So step one, as I said, the approximation bias. So these results are based on error 5. So we studied here, I'm always giving exemplary months, of course. Here's an example for January. We basically, I show you results here for 200 hectopascal. Here's the geostrophic approximation, and here the gradient wind. And here we are in the stratosphere on 10 hectopascal, again, geostrophic and gradient. And what we can see is that actually the geostrophic approximation works quite well in this. Oh, it's okay. In this tropospheric region, we have a little bit of bias, but it looks quite well. And we have this breakdown because, as I've said, the Coriolis force approaches 0. So basically the approximation doesn't work anymore. Also, the gradient wind looks quite well. This is calculated as a bias relative to actually the geostrophic wind. So if the differences are very small, it just means they are very similar, so that you understand that. At 10 hectopascal, we can see this noticeable bias over the polar regions. So when we are in the stratosphere, we have this bias in the polar regions. When we now, that's geostrophic wind, go to the gradient wind, we can see the bias actually decreases. So that's good. So the gradient wind seems to be the better solution. But as you can see, over the polar regions, we introduce basically an additional bias, a negative bias. So this is something I want you to keep in mind. Okay, so let's show quickly the results for the equatorial balance equation. We have here, we studied it in longitude sectors here as profiles. The original error 5 winds, the derived one, and the difference, that's zonal, that's meridional, and that's wind speed. And what we could see is basically in the stratosphere, the zonal component dominates. I mean, we expected this, of course, and the meridional component is essentially 0. Okay, so we can basically use the zonal component, that's enough. In the tropospheric region, we can see that's the computed ones, the meridional component starts to increase. So it's smaller than the zonal component, but still not 0. So it was not so easy actually. It was a bit challenging to compute the meridional component, but still, I would say altogether, it worked, and it did improve actually, because here we do the wind speed estimate. I will show this here as well. Here's we focus here always on a region between plus and minus, 5 minutes? Okay. I'm having a lot more. Plus and minus 5-degree latitude. So we are over the equator. And I studied here the absolute difference of wind speed with the equatorial balance. As you can see, we have a little bit of bias here, yes, in this region. But as a relative difference, because wind speeds are basically larger, it looks quite good. So I would say we are able to compute also over the equator the wind speed estimates with RO. Okay, so now the systematic difference. This is now RO as a difference to error 5. And as you can see, the systematic difference, it's here for January and July, is very small, actually. But we have a noticeable larger systematic difference over this subtropical jet stream. So this is kind of interesting. So this difference seems to be small, but in this jet stream core, we have a larger systematic bias. We actually checked this out. We did a couple of things. I cannot show you everything. Here's a temporal analysis of this larger bias. So we intentionally go in a region where the bias is larger, and we can really see between error 5 and RO, there is in the jet stream core a systematic difference. And it does not fulfill the WMO requirements basically for wind speed. But for me, we checked this also in a vertical cross section. We just noticed that basically the onset of the jet stream is at a different location for RO. It's a little bit towards lower latitude than for error 5. So I think this is kind of interesting. I'm not telling you I have the answer for that, but I think one should be aware of that. Okay. So I give you an intermediate summary. I couldn't show you all the results, but basically what we found in our initial analysis was that the geostrophic approximation really works best in the troposphere. The gradient wind took over in the stratosphere. That were the results. The systematic difference was actually quite small, but we had this exception in the jet stream core. And the equatorial balance approximation, I want to be honest here, was challenging because it's a double derivative, so it's more challenging to reduce the winds. But I think for wind speed, we got a quite good estimate. So far, that's the intermediate summary. But I want to give you an outlook. You know, we now started to include advection to the solution. This is really preliminary work. I want to emphasize a lot of work has been done by Irena Nimac. She did a lot of studies with the equations, with the momentum equations, and also Johannes Unek did a lot of work here. So this is now again based on ERA 5 data. So as you can see, I'm not doing that right. Why is it so high up? Do I do wrong? Okay. Okay. We have here gradient wind at the stratosphere. And we already know that's the better solution. And we have this positive bias, which is not that small. But I told you, there's also, why do I have to hold that up so high? And
on the his screen. If you move it side to side, you might get it back on.
okay, I'm sorry. So we have this negative bias here. And then we included advective transport to the solution. And as you can see, the bias really decreased. So what we basically have is we have the flow, the wind flow is not completely zonally symmetric, but because we have this wave-like pattern of wind flow, as you know, around the globe. And if you include this additional transport, the wind results get much better. So we can really see, and in that this is a really good wind field in the stratosphere. And here we already used the equatorial balance. And the same is true in the troposphere. We have this larger bias patterns here. We have basically wave activity. We have a bipolar bias pattern over large mountain areas like here or here. And as I said, there's a lot of wave activity. I'm sorry. But when you include the advective transports, the results really improve. So I'm quite happy, actually. This was, of course, ERA 5. So if we do this now for RO, it also works. So we have the same story. This is all RO for 1 month on 2.5 times 2.5. And we really can see that we got rid of this bias, and in the stratosphere, the results improved. Here's the equatorial balance. We have a little bit larger biases here. And the same is true in the troposphere with the advective transport on the right-hand side. It really improves. And you have to be aware, if you see the small scale fluctuations here, that's a systematic difference. That's not because we do the approximations. Okay. So I had the idea that we do a map. I thought it would be, we need to understand when is what approximation basically the best approximation. So it's dependent on latitude and it's dependent on altitude. So I suggested we do a map and basically compare it with the original ERA 5 data and see what approximation fits the best at what region. And what we could find is that in the stratosphere, basically it's gradient plus advection, the best fit. And here the equatorial balance. And in the troposphere, we have here the geostrophic approximation plus advection. And here we are still in the stratosphere, so it's again gradient wind plus advection. So if we study this as a vertical cross-section, you can imagine it goes exactly with the tropopause. I think it's really nice to see how this goes. actually. And we have a little bit of an exception in this jet stream areas where actually gradient plus advection would be the best fit. So I'm actually already at my summary now, and I will skip it and give you the conclusion. I personally really think it's possible to derive monthly 2.5 times 2.5 wind fields with RO. And the purpose would be, of course, climate monitoring and analysis. I think it has an added value personally, because it's basically long-term stable. It has this high vertical resolution. Reanalysis also shows these assimilation changes with the data set. So I think it can be an advantage there. And our outlook would be that we now derive three-dimensional wind fields, and we always kind of choose the best approximation dependent on latitude and altitude. That's our next step now. We will, of course, include the advection in the wind field estimate. And I just wanted to say there's a lot going on. I have a little team, as I said. We're doing a lot of work right now. And the money is running out, as it is. So in 6 months, I have no money anymore. So I'm currently also basically writing a research proposal in the hope that it will be continued. And that's it. Thanks. And if you
Thank
want,
you for the nice product, Julia.
we could also discuss in the break. I know it took more time, if you want.
So I would encourage everyone to talk to Julia after the break. This was a very nice talk, a very good product. And I would like to invite Hans Gleisner as our next speaker. And he will talk about ROMSAF climate data records, plans and applications.
Okay, so good morning. My name is Hans Gleisner. I work at DMI in Copenhagen. So these guys here is the ROMSAF team at DMI. So I will talk about our climate data records, and also I will